the answer.
Start sharp. Good morning, everybody. Welcome to this seminar. Thank you all for coming. This is a seminar where we are happy to have Francesc Hernandez Garcia, who will be presenting his master thesis. Just a little background on the work and the project behind it. This is a part of the initial part, the start of a bigger ERC funded project in press, dealing with extreme conditions in matter, in particular in liquids and in gases, and special generation techniques of those. And this is the first result out of the project that Francesc will be presenting to you, in particular how to generate such conditions in those liquids and gases, right? So the title is correspondingly the design and optimization of a pulse power generator for electrical wire explosion. And just to mention also, maybe Francesc is already continuing in this project as a PhD student. Just a little bit of things to complete as a master student. This is the thesis, the first milestone of the project. And Francesc, please, the stage is yours.
Thank you very much, Michael, for the introduction. As he has mentioned, the name of the thesis is Design and Optimization of a Pulse Power Generator for Electrical Wire Explosion, and this thesis has been done for the Master of Science in Aerospace Engineering here at KTH, and developed at the Fluid Physics Laboratory this spring semester. There are two main concepts already in this title: pulse power generator, what it is, it's a system that we are going to be using to experimentally create these shockwaves, and electrical wire explosion. This is basically a phenomenon that allows us to generate these such extreme conditions. So, first, a bit of background. The shockwave group is the group within the FPL, the Fluid Physics Lab, that is experimentally creating the shockwaves. And we are divided for right now into two main labs. First, shock tube lab, as the name indicates, we have shock tube. Here, our colleague Sora is sort of the main responsible, and this is just a diagram of this shock tube. And this is a very reliable system in order to generate these shockwaves. Old, well understood, but it has its limitations. So basically, in the functioning of this, we can generate the big pressures in a driver section, not so big pressures in a test section, if we get atmospheric. And then we release a valve to reduce all this pressure, and this pressure difference creates a shock. So this works quite good in gases. It has limitations in terms of Mach number of the speed behind the shocks. It can also work in liquids, although it's not so common. It's more complex to operate. This is why in the world of shockwave generation, we're seeking for other methods to create this. Another possible method, and this is where our project Impress project comes into play. We're still trying to figure out a name for the lab. It's a pulse power generator. This is the system that we have been studying, or I've been studying for this thesis. Here we have a picture of the test chamber, where we basically can place anything that is a conductor in this place chamber. Ideally, we want something that will explode, will expand abruptly, and this expansion, we're aiming to create shock waves by means of the expansion. In whatever medium we are placing here, it is a test chamber. We can place a gas, we can place a liquid, we can place a solid, we can place anything. Everything is, the explosion is happening inside the medium. So everything that you place in terms of energy will remain in the system. Will either go to the medium or remain electric. until it discharges to the ground. So this system uses electrical energy, which will be stored in big capacitors, as I will explain afterwards. A bit of introduction as well. What is an electrical wire explosion? So electrical wire explosion, we need to think. I mentioned we have a test chamber where we place a wire vertically, and this wire changes its phase from solid to liquid, from liquid to gas, and gas to plasma because it keeps heating up. And this change of phase from liquid to gas, the gas expands abruptly. And it's this expansion that is creating this shock. And this is the first ever taken streak image by Bennett in 1958 of this phenomena. And I may understand that this is a bit hard to understand as it is the picture, but this is a streak image. It's not a typical camera picture where you have a wire, you take a picture. It's not one of those, it's a streak image. In order to visualize or understand what is happening, we need to imagine that we have a wire placed horizontally, and then we visualize a slit of this wire, vertical slit of this wire with a camera, streak camera. Then the slit is moving across the wire as the wire expands, and this creates an analog image. In time, on the horizontal axis, and some spatial component on the vertical axis. In this case, the radial distance, where we can see that there is something expanding in this radial distance in the center. This is wire, plasma of the wire that is expanding after the explosion. And at the beginning, we have evidence already that there was a shockwave being generated. So this was 60-something years ago. And yeah, well, from then until now, there's been a lot of improvements, of course, in these methods of streak cameras and the understanding of this phenomena. But this was the first evidence already. So the initial status is that we built one of these PPG systems in this laboratory. And from then we ask immediately the question, how do we use this system? How do we how do we determine the initial conditions and parameters to efficiently create it? Is mainly the answer that I've been trying to answer in this thesis. A bit of state of the art. This is another streak image, much more modern of what is happening. Before we just had light. This is a shadowgraph image. So this is why we can see the wire here already. We're seeing the shadow of the wire. And there we have time and radius. As we see, we have a wire. At some point, it sublimates, goes to gas state, creates plasma because it's very hot. This plasma expands in the center, and there's a shock wave being generated at the beginning of this expansion. So a very strong shock wave, but you'll see afterwards because the wire is very thin. So this is a very complex nonlinear phenomena. I want to argue why. Because it's not just solving the conservation equations of the fluid, but in turn we have huge currents flowing through the wire. These huge currents are created via a potential difference. In turn we have an electric field there. The electric field changes in time, which via Maxwell's equations induces an azimuthal magnetic field. So we have a mix of physics there between fluid mechanics and Maxwell equations, that in order to understand what is happening here, we will need to solve as well the Maxwell equation. This is called the magnet of hydrodynamics. So it's not just a hydrodynamics problem, but it's bonded with the Maxwell equations. So furthermore, if it's not complex enough, we already have other phenomena such as skin depth effect. And I want to explain what is this, because it's conceptual. It's going to be conceptually important in the end to justify some of the phenomena that we observe. Basically, the current through a conductor tends to flow in the surface of the conductor. Why is that? Because simply the resistance is smaller there. So the current tends to flow through the surface. And if the current flows through the surface will sublimate faster than the core of the wire. This will create a non-uniform explosion. So this will decrease in the end the efficiency of our electrical to mechanical energy transformation. Before going to methods and results, I want to just give a bit roughly the theoretical background. So in order to estimate the pressure behind the shockwave, we've been using the shockwave relations. And this one's for air, are very well known, the perfect gas equation. quite straightforward to obtain these equations. These are the thermodynamic parameters in front and behind each other. And in water, this is harder because water is an incompressible fluid where we need the equation of state in order to solve the 1D conservation equations for in this control volume. And this equation of state is it's the Tate equation. In this case, in this form, it's modified by Sally in 1988. And this state equation is simply a relation between pressure and density in water. Tate, I want to mention that it's a Scottish mathematician in the 19th century. So by using this equation of state and the conservation equation of the fluid, it's possible to obtain this highly nonlinear 8th order relation for the density behind and in front of the shell. Once you get the density, you can come back to Tate, equation of state, and estimate the pressure. And this works quite good. If you compare with tables with actual values, gives the value that it should give in terms of pressure. So if it was not complex enough, I mentioned that this is an MHD problem. Sort of explain or justify then what it's an MHD problem. Here we have the equations of motion, the governing equations of this phenomena, MHD problem. This is a one-dimensional model in differential form, where I just want to argue that the momentum equation is being affected by this cross product between these electrical and magnetic fields, as well as the energy conservation equation. So there will be this electrical field, by means of this term square, will affect the mechanical energy of our shockwave, or the flow in general. And these two are related via the Ampere's law, which is one of the Maxwell's equations. So this is just a 1D model. If it was 2D, 3D, we need to consider it will be even more complex, because you need to ensure that the Maxwell equations to solve them is not so straightforward. So I want to also mention that aside from solving this, you'll need to solve the electrical circuit, because the current is indeed creating an electrical field. And in order to estimate the current, you'll need to solve the electrical circuit of the system, of the PPG pulse power generator. And this electrical system is by itself nonlinear and time dependent, because the resistance and inductance of the wire change in time as the values of the wire increase. It's a really highly complex and nonlinear phenomena involving different fields of physics. I want to describe now what are the methods used to generate this explosion. So you enter the lab and you find yourself in what I like to call control room, where we have computers, we have everything from where we can control the explosion. And you keep walking in it, and you find yourself in the test room, where we have the machine and the system and everything, the explosion is carried out. So this is the 3PC. You can see a little on the right, a bit better. It's a vertical structure with 4 capacitors at the bottom, huge capacitors, a total capacitance of 10 microfarads, that will store electrical energy for this wire's explosion, so up to 23 kilovolts. And then these capacitors will discharge this electrical energy through an electrical circuit that is inside of this plate, vertically through this test chamber, where we place the medium and the wire. Here you can see some optical parabolic mirror to redirect the light of a laser through these windows that will go to a camera. And using shadowgraph and Schlieren, which I will introduce very briefly later, we can record the explosion. So inside of this box, what do we have? We see a very simplified sketch of what is inside, but we have the 4 capacitors. Here at the center, we have the main electrode. And I want to mention that in order to discharge the electrical, the voltage that we have there in the capacitors through this, to this main electrode, we have what is called the spark gaps, these 4 spark gaps. And this spark gap is nothing else than a dielectrical discharge. Dielectrical discharge, you can imagine, like a lining. It's the most similar common physics that everyone knows. Basically, you create a voltage difference, and the medium is not able to support this voltage difference, and you create a dielectrical discharge, which in this case will be a plasma channel that in time will be diffusing in the air. With this plasma channel at the beginning, we conduct a lot of current, and as it diffuses, it will increase its resistivity or increase the current that it's flowing through there. So by itself, this electrical circuit is another time dependency. These spark gaps are also time dependent. It's not just the wire that's expanding, changing the electrical parameters, it's also the spark gaps. Keep it all you need. Well, it's fine. Fine. So with the description of what is in the system, here it's a table with the hardware. Just the most important thing maybe to mention is the high-speed camera reaches 10 million frames per second. In this thesis, we haven't been up to 10 million, but we've been using 5 million frames per second because it was just not necessary to go up to 10 million. And then this is a diagram involved explaining everything that is happening in the room. But basically, I want you to imagine that you are in a test room and you need to trigger the explosion somehow. The explosion is triggered with a delay generator manually. You press the button and you send 3 trigger signals. One to the laser, one to the camera, which in parallel will be synchronized, and one other trigger signal to an external trigger circuit, which by itself is an electrical circuit, a separated box in the lab. And this trigger circuit sends a huge pulse of voltage, 70 kilovolts in the order of that, to the pulse power generator, activating this discharge through the spark gaps. And then the explosion starts, and we are able to record it with the laser. So I want to mention as well, these elements are inside of Faraday boxes, power supplies and camera, just to protect them from the electromagnetic radiation that's being emitted in explosion. Final slide regarding methodology, optical setup. We're using Schlieren and shadow graph, Schlieren in air and shadow graph in water. And this is a basic simplified sketch of the system. It's a set-type Schlieren system where we have a laser emitting light to a parabolic mirror. This is the parabolic mirror of the image I showed before. This parabolic mirror collimates the light through a test region, where a test section where the explosion is happening. This explosion creates changes in the density in the medium, and these changes in density deflect the light rays. Basically, this light ray deflection then are captured as shadows in a camera. And we have second parabolic mirror converging the light through a knife edge in case of Schlieren to the camera. And in front of the camera, there is a lens in the light properties. So this is a picture of this section. This is second parabolic mirror that is redirecting the light. Here there is a knife edge. It basically cuts the light there. It's not going straight to the camera. And the lens, and this is the Faraday box where the camera is. An image of the camera, the Mach 2, HPVH2, up to 10 million frames per second. And then the two typical images, this is a Schlieren, where we can see a bit more resolution and details of what is happening. This is in air, but it's less focused. And then this is in water. We see less things, we only see pragmatically shadows, this shadow graph, but it's a bit more focused. Now, in terms of results, the results have been divided into sort of sections. Right? First, the electrical characterization. Well, I don't want to enter too much in this thesis, in this presentation. At least if you want to know the details, you can ask afterwards. And then the shockwave generation. So for this electrical characterization, I just want to mention that the PPG has been modeled as an RLC system with time-dependent resistance. And this is the analogy, the RLC system, which has been modeled both analytically with the analytical equations, this RLC, just straight solving the second order governing equation of the electrical system, and numerically with a spice solver and a software called LT-spice. So we solve these models, and we are able to compare the waveforms of these models with experimental waveforms obtained from short circuit experiments. Short circuit experiment is simply, instead of placing a wire, you place a rod that doesn't explode. So if it doesn't explode, the current, it's a closed loop. It's like this electrical. And here we would have a wire that it would explode, so the current will stop flowing, ideally. But instead of a wire, we place a rod. So the current is closing the system, going to the ground again. And via this analysis, it's possible to find these electrical parameters. We have also been able to find the transformation factor of the Rogowski coil used in the lab. I haven't explained what is a Rogowski coil, but it's basically the element that allows us to compute current. If you want to know details, you're welcome to ask afterwards. And these are the waveforms obtained in short circuit. As you can see, it's a damped system where the currents achieved are in the short circuit experiments, right in the order of 300 kiloamperes. It's a huge current. And the voltage is, this is for a initial capacitor voltage of 24 kilovolts, and we start at 24 and we just discharge. So let's start talking about shock wave generation. I'll show you a video, but what we have in here is a wire placed vertically. This wire is supported on its top to the ground and on the bottom to the main electrode, from where the current is starting to flow. Then we load these capacitors to 23 kilovolts. This is in water, 5 million films per second. We press the button and we leave the system.
We run.
Yeah, exactly. We leave the system go. Let's see what happens. I'll show you the video. All the videos 15 microseconds. Play this again. And what you can see in the middle, it's plasma expanding. This is the shock wave going away. From top and bottom, something is being created. And then at the end, it will be a reflection. When this shock wave arrives to the wall, it reflects back in. So it's better, there's a diagram of what is happening, right? So I explained we have the plasma, this is the wire. After the explosion, it becomes plasma, super hot, it keeps expanding. This plasma is still conductive, so it allows for current to flow through the plasma. The shock wave has been generated at this initial expansion of the wire. These are speeds, the shock rod is moving at 2,500 meters per second, because this is in air, so it's slower. This is in water, sorry. In air, we have achieved the speeds of 6 kilometers per second. So huge speeds, very fast. The pressures behind the shock are in the order of 17,500 bar. It's a huge pressure, so almost 18,000 times the atmospheric pressure that we have in this room. The undisturbed water, then the secondary shocks that just justify what they are in the supports on top and bottom. There are some dielectric small sparks being created there that in turn also create these secondary shocks that come from top and bottom and interact with each other. These ones are weaker. This is the main shock, but it's being created by the wire. These secondary shocks are being created by sparks. And the surface limiting or separating these two mediums is called complex wires. So in terms of time scale, as you can see here in 1.2 micro, actually less than 1 microsecond, everything is already there. We have the plasma, very hot now at the beginning. As it will expand, it will cool down. But right now at the beginning, it's very hot. This is why it's white. The shock wave is already there. You see this black area. And then the system simply evolves in time. So everything happens very, very fast in sub-microsecond scale. In terms of results, now we have these nice videos. We create 12 wire explosions, 3 in air and 3 in water and 9 in air. In water, it's been done for wires of 150, 400, and 500 micrometers for an initial capacitor voltage of 23 kilovolts. And in air, the same wires, but for 3 different initial capacitor voltages, 19, 21, and 23 kilovolts. In order doing it this way, we were able to see what's the behavior of the system, both changing the initial voltage in the experiment and changing the wire length. So we get these 12 nice videos. We are able to track the position of the shockwave in time. These are for air and water, 2 of these explosions, correspondingly to 500 micrometer wires at 23 kilovolts. And this dark black line with these dots are the experimental results just obtained from the camera. This is the position in time, and for air and water. Then once we have position in time, we can take the derivative, find speeds. So the speed is these yellow lines coming from the top and decreasing in time. In air, we're talking in orders of magnitude of 6 kilometers per second. In water, it's a bit slower, but still huge velocities. And then with this speed and the shock wave relations, we're able to estimate the pressure behind the shock by using the shock wave relations that I have introduced before. The pressures in air are smaller, 360 bars for the explosion, but in water, we're talking about 18 kilobars. Huge pressures. So once we have this, we have the initial speed of the shock wave, or in other words, initial Mach number. I can plot these 12 explosions, the 12 initial Mach numbers in a diagram like this. Not like this, where we have the 3 different wire diameters for 150 air, these blue lines, Mach number on the left, 400 and 500, and for water, Mach number on the right. What we can see here, this is very relevant in terms of concept. So there is a peak in the Mach number of air. So increasing the wire diameter doesn't give a more efficient shock wave, at least in terms of generated Mach number and strength in air. And this peak is being delayed in water. At least we haven't observed it experimentally, but it has to be there in the sense if you keep increasing the wire diameter, at some point there will be no explosion at all. But it has to decrease, but it will come afterwards. And we will argue, we will discuss why in the following slides. So before going to that, there are also oscilloscopes with high voltage probes measuring current voltages going on in the experiment. And these are plots of the voltage on the left and currents on the right. Air on top and water on bottom. For 3 different wire diameters, the smaller, the medium, and the larger wire diameters. These are the colors, blue, red, and yellow. So we can see there's a voltage spike, and the current is doing their things. We have a first peak in current, and then a second peak called V-strike. I want to argue why that happened. So first, we have a wire in solid state. We start discharging current, heats up, goes to the liquid, keeps heating up, goes to gas, and then the conductivity of this gas is much smaller than the conductivity in the liquid. So this decrease of conductivity decreases the current flowing through the wire, and as this current decreases, since the power needs to, at that instant, this is differentially will remain constant, there needs to be a voltage spike, just to compensate. This is what is happening here. This is voltage spike at this first decrease in the current. And in between this decrease of current and this voltage spike, there needs to be a maximum in power. We have almost the maximum power achieved. The maximum current, it decreases the current, there's a spike in voltage, and somewhere there in the middle there's a peak in power. So we have voltages, we have currents, we multiply both, we get power, we integrate power, we get energy. Let's see how it looks like. For wires, 150, 400, and 500, the blue lines are, these are all in water, 23 kilovolts. The lines on the left are power, and these red orange lines are energy on the right. So I want you to see that this peak in power is associated with the time of the explosion. We're not sure up until how accurate is this, but it is close, at least to the initial time which is shock wave is being generated. So this is a time characterizing explosion. And then when there is this peak in power, there is a deflection point in the energy. You see that the order of magnitude of the power, 3.5 gigawatts. Just for a reference, a typical nuclear reactor is giving 1 gigawatt energy, 3 times greater. But we need to consider that this is a very, very, very short phenomenon. So this is why it is so huge. Because if you see the order of magnitude of the energies, 2 kilojoules, not so much. It's not a matter of how much, it's a matter of how you discharge this energy. How fast and how do you concentrate? The more concentrated, the greater the energy, and the faster, everything will be more powerful. So we get the energy until the time of the explosion. which we can plot as a function of the wire diameter square, or since all the length of the wires are the same, the volume. In this plot, you can see that we have sort of something in direct proportional to the volume and the electrical energy until the time of explosion for all the 12 explosions that we've carried out. We see that this looks the same. It doesn't matter if it's air, water, doesn't matter initial capacitor voltage. This looks like a straight line. At least with experimental error in this range of results of the experiment that we've carried out, it is a straight line, or similar to a straight line. So if this is a straight line, what is the slope? Is the value of the slope of how the electrical energy changes with the volume? This is the value. So we're saying here that for a given wire, the electrical energy that is going to be needed to explode it, it's independent of the medium and initial capacitor voltage. It just depends on the wire. So if this is a constant, what can we say about the volumetric electrical energy density, or the electrical energy per unit volume or mass of in this copper? So we can do a quick and short mathematical derivation to get to an equation like this. And the relevance of this equation is that this is an asymptote as volume increases, where the value of this asymptote is exactly the same as the value of this slope. This means that as we increase the wire diameter, at some point, we are not giving more energy, electrical energy per unit mass, per unit volume to this wire. Actually, a wire of 400 micrometers is already giving around 95% of the maximum electrical energy that we can give to this wire. So more is less in this case. If we go greater than this, we're increasing a lot the volume, we're giving much more mass in this wire. It's not needed. All this, very good, explains electrical behavior. What can we do about the mechanical energy? How do we estimate the mechanical energy of this topic? So there are some analytical models that I don't want to discuss now, but if you have some questions, you can ask afterwards. Although these analytical models have proven to not be applicable in our case. So we have thought directly of doing CFD, but the CFD, the problem is that it doesn't simulate the magnetohydrodynamics. It doesn't take into account these dampers alone, these electric fields and the magnetic fields being created that in turn also affect the mechanics of the energy in the system. So then we say, okay, let's do an MHC, but that system of equations that I have introduced you is 1D, so it's already a simplification, and to solve it, it would be already a math statistics. It's out of the scope of this project. So we have come at some point where with our ideas, and we said, okay, let's do just basic mechanics. Let's have a wire that is expanding, and as it expands, it's modifying, compressing the medium, creating a shock. And this in this TX diagram can be seen as we have a piston, something that is pushing the medium. And as this piston accelerates, it's sending compression waves that keep accumulating to increase pressure. And when this pressure is strong enough, we create a shock wave. So if we have the acceleration of this wire, we know the mass of the wire. We can multiply mass times acceleration, get a force, and integrate it to get the work done by the wire as it expands. Okay, this is what we've done. This is a hypothesized acceleration of the wire, which changes linearly inside the wire, and the contact surface is moving. In order to estimate this acceleration, we're using the speed of the gases immediately after the generation of the shock wave, behind the shock wave, divided by this time characterizing expression. And if we plot this, I don't want to go much into the mathematical detail, but if we plot this, this is the shock wave being created, and this is our wire. It clearly needs to move slower. It's expanding slower than the shock wave. And during this time, similar in magnitude to the time of explosion, or to the peak of power, is affecting strongly the dynamics of the explosion. Still, as you can see, this is accelerating the shock wave until this point. From here on, it looks more or less independent. So, though we're taking this acceleration, we get force, we integrate, we get work. This is the equation, how it looks like. Basically, we already see here that the fastest equation is the greater movement work done by this function. So the work of this wire expanding is highly dependent on the dynamics of the expansion, how fast it happens. So we get mechanical energies, we have transferred electrical energy, we can plot them in a graph. How much electrical energy corresponds to the mechanical energy? Well, this is in air for the three different voltages, greater voltage on the top. As we see the increasing the transfer electrical energy or increasing the wire diameter actually increases the total mechanical energy given to the medium. It looks like it has an asymptotic value, but it has not improvement. Simply, it keeps increasing. So this looks into contradiction to what I said before, that there is a maximum there in the Mach number. But it just looks in contradiction because the Mach number increases with the pressure behind the shock. And the pressure behind the shock is nothing else but energy density. It's not total energy, it's energy density. So if we divide this mechanical energies by the volume of the wires, we see that clearly we have a peak in 400. So that equation that I showed before is being able to show that we have a peak as well. This is an indication that it's working well. I want to discuss now why do we have this peak? Why is it relating water? The reason of this peak, we think that it's because of this skin depth effect that I have explained before. Basically, as we increase the wire diameter, this current will flow more through its surface rather than through the core of the wire, which will decrease the efficiency of this flow. And if we compute this parameter delta, which characterizes the skin depth effect, this delta means that the current from surface to this distance delta from the surface, it's increasing up to down to 33% of the value of the surface. So it's distance characterizing, this skin depth effect is around 500 micrometers, which if we multiply by 2, because we're talking about the wires in the cylindrical wire, and this would be 300. So in other words, wires bigger in diameter than 300 would have a relevant skin depth effect. So the current will flow in a relevant way through its surface rather than through its core, which in turn will decrease the efficiency of expressions. And this is right here in the middle. So from here on, this effect starts to develop. This is why we argue that this could be the reason. Why is it dilating water? Simply because what's the main difference between air and water? It's the compressibility of the medium. If we define compressibility like this, which is dependent on the type of process, but it's in order of magnitude, it's sort of 5 orders of magnitude smaller in water than in air. And this is relevant because when you create a work inside the medium, this work will go to increase pressure, but not to create kinetic energy in water. In air, this is why the pressures in air are smaller than in water, basically because this work in air goes to create kinetic energy, not so much to create pressure. And in water, it happens the other way around. So this is why this peak is being delayed, because the work of the expansion is creating pressure and not kinetic energy. At least this is what we think it could be happening. All the reasons, radiation losses, heat transfer mechanisms, internal medium takes heat in a different way. So as a conclusion, just mention that all the goals of the project have been achieved. The main goal was well, to understand how to use this system to create efficiently these software. So this is exactly what has been done. And then we can conclude as well orders of magnitude, which are relevant. Huge pressures can be achieved, huge, as you've seen, powers in the order of gigawatts. We saw that we have a peak. So we saw already that we have an optimal configuration. We have explained why is there and how to characterize it in terms of energies. And then the mechanical energies, this electrical to mechanical energy transformation. Its efficiency is between 12 and 33%. And this matches well the results from similar literature and similar studies. So this indicates that the equation that we came out to compute this mechanical energy at least gives correct orders. Improvements on this work, clearly we need an MHC simulation, including this electromagnetic effects to the fluid. And then we also need to improve the methodology. Why? Because all these experiments are very time consuming. Especially what comes next immediately after this is instead of having one wire at the center being exploded, now we are aiming to doing completely the opposite, having many wires in an array and exploding them in order to create a shock wave that will concentrate energy at a focus. This is called shock focusing. We have built this sort of electrodes where we have 32 wires placed in a cylindrical geometry. And then we will explode this and create this shock which will focus at the center. And doing this is very time consuming. Like we can spend the day just preparing this array. And we need a better methodology. Direct applications of this, really shock focusing, and this of course can be used to study any material under very extreme conditions, talking extreme pressures that you've seen before. Treatment of materials, this in this lab also will be used for the study of cellulose nanofibers. And investigation of nuclear fusion. This, there are no short-term plans to do it because of safety. But clearly we are compressing something. If instead of water it's nuclear fuel, then we can imitate or simulate this inertial confinement methods. And to end this presentation, I want to show, and I know that you want to see this thing exploding, so I'm going to be showing. It is very preliminary. But we see that we have something cylindrical. We're watching the array from here. The array is placed horizontally. And there's, as it explodes, there's a shock being created and focusing at the center. And this, instead of decreasing the thermodynamic properties, it increases them. Why? Because the energy is being concentrated. So this was all the presentation. Question, comments, anything. You're welcome to do it here or through my email or LinkedIn. And I want to thank you as well, Michael and Sebastian, for the supervision and review. Nicolas Albacidis for all the help, and my PhD colleagues, Shinji and so, especially for the help in the loop. So thank you.
Thank you. I hope you can understand that having 3 nuclear reactors, we were happy enough to continue working. Yes, do you have any questions? Yes, there.
So 2 questions. First of all, at the beginning, you said that you plan to you could also use a solid as a medium. But then, like, would you have to drill a hole in the solid exactly the size of the wire, or would you be happy to have a little bit of a gap, and then but then you would have an interface, and what would happen then?
To be honest, I think that the better the contact is, the better it will create or compress the solid immediately after it, right? Okay. So it needs to be in direct contact with the solid. We haven't done this, so I'm not sure of the methodology details on how this could be done. But there are studies that actually are cited in this, in the thesis paper where they do this. Although explaining this, even these studies are not clear about this. I understand that they want to keep something for themselves. But clearly, the better the contact is with the medium, the better it will compress it.
Can you go to the slide? I think it's 14, the one, the first one where you show experimental data. Yeah. So in the top right, the circles are your data, or is it also the dark line that joins them?
Yeah, the circles are direct points.
Yeah.
We have a video.
Yeah.
We measure where this shockwave is.
Okay.
Simply, we have the circles, the experimental data, and the line is just a fit.
Okay.
In this case, a second order fit, it was matching quite well.
And all the other lines
complicated.
And all the other lines are from, you use the velocity distribution, I guess, to obtain the other quantities.
Which one?
I don't know, pressure.
Once we have this estimation of the position in time, we take the derivative, we get speed.
Yeah.
This is why it's so linear, because it's taking the derivative of a second order polynomial.
Okay. So
and then from speed we go back to shockwave relations and compute pressure.
But then the question is, if you go to the side of the video, then
We want to see the video again? Or?
Just the first frame, that one. The wire doesn't look 100% straight.
Yeah.
So your assumption of a 1D flow is a bit low, or?
Yeah, definitely. How accurate are we in computing the position of the shockwave in time? If we have created an algorithm that computes the position of the shockwave in both directions and averages them.
But that would be easy. We just track the position of the pixel and move it horizontally. But I mean, the wave will not spread.
Yeah, ideally, we want this to be super straight to get this perfect experimental data. But we also don't need this level, of course. Okay. Like we know that for this thesis, why do we need this level? In the sense that if we average the position of the shockwave and we create an algorithm that it's more or less efficient, we can estimate already what is the peak of this shockwave. I think that improving this algorithm, of course, will improve the position of the wire in time, which indeed will give more accurate values for the speed of this shockwave, but it wouldn't change too much. We are talking about 6 kilometers per second, and that is the magnitude relevant for estimating pressure. So if it's 6,050 or 5,950, wouldn't change it too much. Thank you. Bye-bye.
Any more questions? Just be near the Zoom people also. But first, yes, please.
Maybe you mentioned the volume of the chamber.
I don't know the number by heart.
And do you know what the maximum pressure it can handle is?
Yeah, it will handle. We haven't had any problem. Just with the window, there we had some problem at the beginning.
Yeah.
Because it was made out of aluminum. And we had to change the windows to make them steel, because after some explosions they started to make.
Yeah.
So that we haven't had any problems because it's huge walls.
Yeah.
But if at some point we see that it started having some deformation, we will then modify it. And we are also, these experiments, now we have medium in all the chamber, but we're aiming to just have capsules, to have less water. We are just interested in having enough water to see what is happening, or enough of the medium to see what is happening. And it's for some experiments, especially for these capsules, for this shock focusing, that it's going inwards. It's not necessary to have all the chamber filled. Yeah. So if we do that, we will decrease the stretches seen by. Yeah. Thank you. Sophia?
How did you decide on the wire diameter? Because for water, you were like perfectly at peak. Did you do calculations before?
Well, we were aiming to get perfectly at the peak. We're not sure if we are perfectly at the peak.
No, but like you captured the peak in your.
Yeah. That was basically experimental. Okay. Experimental. So when this project started, we didn't know anything. It's just let's do an explosion. Let's record something, and then we'll see how we analyze, and if we see that this is efficient. If nothing is being created, if something is being created, we saw that for wires of 150, already some good efficiencies are achieved. And then from here on, we keep increasing wire diameter and keep it. So in fact, it was very trial and error, the process. I guess.
One more question regarding when the plasma is formed. Is that the point, might be a basic question, is that the point when the shockwave is created? Like you get that results peak of is it 2.5?
No, it's definitely not a basic question. This is something that it's not so clear at the instant of when this shockwave is started to be created. Because we have, from solid to liquid, the solid is expanding, then we go to liquid, the liquid keeps expanding already, not so much as when we are in gas state. And there it's already compressing the medium. There's already at least some compression sent like to the medium. And then we change to gas, where there's an abrupt expansion, and there we can show this trick image here. Here we see already some compression already in this expansion. This solid going to liquid, it keeps expanding, and then when it changes to gas, there is a stronger shockwave being created because this change to gas the gas is much easier to expand. Just that, and then it's both interact to create a disinclination point. That's how this author called it. but it's not so clear, and it's not so clear to link it to the electrical waveforms.
Right, but you had that slide, I don't recall which one it was, where you showed, okay, at 1.2 microseconds, we already have basically all the states. You could already see the shockwave. Did you nail that down a little further? Look at like 0.5 and see if the shockwave was already there, just for experimental observation, or is that too?
Yeah, the shock starts more or less at the time of the peak.
Okay.
So everything is recorded there because every 200 nanoseconds we have an image, and we record. We see how it's very hard to see the expansion of the solid, the wire at the beginning, because that happens way too fast. But the first stages of this shockwave generation, it's seen. Happens in less than 1 microseconds, and we have 2-3 points there.
Any more questions? Let's ask, I don't know,
Questions?
Zoom people, if you have any questions, that's a good time to ask. We have 13 participants. No questions.
You're welcome to talk in any moment.
Yeah, you can talk, you can write.
I have a question.
Yes.
If you go to the last slide where you showed the explosion of all the wires on the side. So we see in this video, yeah, so we see that, it's kind of collapses to the middle. Now, I'm not sure what happens here. I mean, is it shockwaves kind of reflecting back and forth in between the wires, or what is exactly happening?
So we have an array of 32 wires placed in a cylindrical geometry.
Yeah.
So when one wire is exploding, there's an explosion. So it's the same as the video, the wire going vertical. It's happening the same in every single wire. But then these shockwaves interact with each other, creating what is sort of a cylindrical geometry in a shock that, as it converges, it looks, the more wires you have, the more like a cylindrical shock it would look. So that's why it's happening. So we have 32 wires exploding, every single wire of them. And then the interaction between these shockwaves is close to a cylindrical shock. And as it converges, it looks more and more to a cylinder. And then goes to the center focus, and there it's when we get the bigger or the higher thermodynamic properties.
So how accurate can you get that focal point where you generate in the shockwave and from like explosion to explosion, like will it diverge a bit and picking where you put the what you're testing, right? Would that be a problem?
I mean, if all the wires were perfectly straight, same diameter, put in the same distance, if everything was ideal, the center would be the center of geometry. Nothing is ideal. It's ideal. So whether this is a good question. Actually, these are all very preliminary results that were obtained 2 weeks ago. We haven't done much enough of this yet. But I figured that first approach would be to take the middle geometry. At least when it converges, you see exactly at the end of the convergence going to this point. That point could be taken as an initial approach, at least. And then we'll see how, if the center is moving in time next year, to be honest. Maybe.
It will be pain, but we will do our best. Yes?
How is this set up electrically to make sure that the current goes through all the wires at the same time?
So this is this drawing that I made here. I have a pointer. So I have 2 electrodes, and this is placed horizontally with the windows. That's what's happening. Right? There's a holder that is holding this electrode, and then the holder basically makes it possible for the current to go from the main electrode, the plate of the PPG system, goes through this holder, and then the holder is sort of holding this cylindrical piece from its outside. And then it basically sends all the current this cylindrical piece, which is made out of steel, and all the current comes from outside and is redirected through the wires. So it's a good question. This is not easy to design and to come up with a concept that makes it possible to redistribute this current as uniform as possible. And we thought that a good idea was to send the current through the surface.
Okay, so they're all connected in parallel.
Yeah, all these wires are connected in parallel, and they are soldered. Well, in other stuff.
Yeah.
Any more questions? No, I think it's enough. We did a good job. Thank you all for coming. Thank you for the great discussion we had here. Many questions, showing huge interest, I believe. You have a great day. Thank you all for coming. We thank the speaker once again. Thank you very much. Very good.
So, but yeah, so we got for the 3 air explosions at with the feedback, we consistently be consistent about